In section 7.2, we're looking at radical expressions and functions. First thing we want to talk about is square roots. If x is a non-negative real number, then the square root of x is the non-negative or principal square root of x. In other words, the square of a square root just gives me x. So the square and square root essentially cancel. Let's talk about higher order roots. If x is a non-negative real number, then the nth root of x is a non-negative nth root and has the property the nth root of x to the n is just x. If x is a negative real number, then when n is an odd integer, the nth root of x has a property that the nth root of x raised to the n equals x. Or when n is an even integer, the nth root of x is not a real number. So what this is saying is essentially we can expand our rule with square roots with an nth root. So if the index on the root is the same as the power, they're going to cancel and just give us what's underneath the radical. But if our piece underneath the radical is negative, we have two choices. If it's a negative real number and our n is odd, then it can cancel out just as it does beforehand. But if n is even, then this is not a real number. So let's take this to the test here with example number 1. We're looking for the cube root of negative 216. So what cubed gives me negative 216? Well, negative 6 cubed gives me negative 216. And so that means that the cube root of negative 216 is negative 6. What about the fifth root of negative 32? What raised to the fifth power gives me negative 32? Well, negative 2 raised to the fifth is negative 32. And so the fifth root of negative 32 is negative 2. Now we can evaluate the negative underneath the roots because my index has been an odd number. But for part C, I'm looking at the fourth root of negative 16. Since our n is even, it's 4, and x is negative, this is not a real number. If I raise a negative to an even power, I'm still going to get a positive number. So that's why this is not a real number. And for part D, the same idea here. We're looking at the sixth root of negative 64. My n is 6, which is even, but my x underneath the radical symbol is negative. So this again is not a real number. Now let's talk about the domain. The domain is the values of x, or my inputs that I am allowed to put in to the equation or the expression. So let's take a look at the square root of 3x minus 6. So what we found from beforehand was we were not allowed to have a negative number underneath the radical symbol when my index was even, which a square root has an index of 2. So what we need to make sure is that the expression underneath the radical is greater than or equal to 0. So we have 3x minus 6 is greater than or equal to 0. And now we want to solve. So let's go ahead and add 6 to both sides. And so we have 3x is greater than or equal to 6. And then we want to divide by 3 on both sides. So we end up getting that x is greater than or equal to 2. And so the domain is all real numbers. X, where x is greater than or equal to 2. Now let's go ahead and look at a cube root. Well, a cube root has an odd index of 3, and it didn't matter what kind of value I had underneath the radical when the index was odd. I could have positive, I could have 0, or I could have negative values. So in this case, the answer is all real numbers. And for the third one, we have the square root of x minus 2 squared. Well, what ends up happening is that the square root and the square cancel, and this just becomes x minus 2. But the domain of x minus 2 is all real numbers, because I can plug anything I want into this. Let's go ahead and talk about rational exponents and radical form. If n is a positive integer and x is a non-negative real number, then x to the 1 over n is the nth root of x. So the denominator becomes the index, and the 1 is still the power of x. That does not change. So let's go ahead and rewrite example number 3 with our rational exponents. So we have the cube root of x squared. Well, the only thing that happens is the x is still raised to the 2, but now the denominator becomes the 3. We just move the index back as the denominator of our power. Same thing goes for part B. Even though the 7 is on the outside, it works exactly the same way. So our w is going to be raised to the 7th over 5. For positive integers m and n, and any real number x, for which x raised to the 1 over n is defined, we have x to the m over n is equal to the nth root of x raised to the m, or n, the nth root of x to the m. If it is also true that x does not equal 0, then we can have x raised to the negative m over n, which just flips it to the bottom of our fraction, and then the rule still applies that we just defined above. So let's go ahead and look at example number 4. We want to change to radical form and evaluate if possible. So we have xy raised to the 5/7. The denominator becomes the index on our radical, so this is now going to become a 7th root. And then our xy is just raised to the 5th. And so what we can do is we can raise both the x and the y to the 5th power. So what we end up getting is x to the 5th and y to the 5th underneath our 7th root. Let's go ahead and look at the second one. This one's a little bit tricky because only the x is being raised to the 3/4, not the 3 and the x. So the 3 is still going to stay on the outside. And then as far as the radical portion goes, the denominator is the index. So we're going to have a 4th root of x cubed. For negative 16 raised to the 5/2, the denominator is going to become the index. So technically this is just a square root, but you can see where it's coming from. And then we have negative 16 raised to the 5th. But that's a negative raised to an odd number, which means we're still going to get a negative underneath a even root. And so this is not a real number. And 144 raised to the negative 1/2. The first thing we have to do is flip it to the bottom of our fraction. So we have 1 over 144 raised to the 1/2. And then we can go ahead and rewrite this. So the denominator is now going to become the square root of 144 raised to the first power, but that's just 144. And the square root of 144 is 12. And so we end up with 1 over 12 as our final answer. Now for all real numbers x, including negative real numbers, the nth root of x to the n is the absolute value of x when n is an even positive integer, and the nth root of x to the n is equal to just plain old x when n is an odd positive integer. So for example number 5, we want to simplify, and we're going to assume that x and y may be any real number. So either positive, negative, it doesn't matter. So for the square root of 49x squared, we're going to look at the square root of 49, and we're going to look at the square root of x squared. Well, the square root of 49 is just 7, but because this is an even index, that means we need to use the absolute value bars. And the square root of x squared, the square root and the square cancel, and we're left with just 7 times the absolute value of x. Let's go ahead and try another one. We have the 4th root of 81y to the 16th. So same idea, we want to look at the number and the letters separately. So that's the 4th root of 81, and then the 4th root of y to the 16th. And so the 4th root of 81 is 3. We want to use our absolute value bar again because our index is even. And the 4th root of y to the 16th, remember we just moved this index as the denominator, and 16 over 4 is 4. So we end up with 3 times the absolute value of y to the 4th. Let's go ahead and do one more. The cube root of 27x to the 6th, y to the 9th. So we're going to go ahead and split this up. The cube root of 27, the cube root of x to the 6th, and the cube root of y to the 9th. And so the cube root of 27 is 3. And because our n is an odd integer, we don't need the absolute value bars. And so we end up with x to the 6 over 3, which is x squared, and then y to the 9 over 3, or y cubed. So our final answer is 3x squared y cubed.